We've been going through the problem-solving strategies. We're now on step 2, where we're going to be evaluating the enclosed charge. In the previous lecture, we did step 1, picking a good Gaussian. So here we go. Step 2, evaluating the enclosed charge. We mainly have constant charge densities. With very few exceptions. So I'm going to focus on constant charge densities. So then the big question that we have is, how do conductors and dielectrics distribute charge? About their surfaces. So that's a really important question. So picture-wise, we have to think about the following thing. So a charged conductor, and I really want this to stand out, and I'm going to highlight this in some color, places all extra charges onto their surface. With no extra charges inside. So we're talking about a charged conductor. These charges repel each other and spread out uniformly. On the surface. With a constant charge density. So picture-wise, I imagine something like this. So I have a sphere, and we're going to say it's a conducting sphere. And so when I have a conducting sphere, I'm seeing that all of the charges are on the surface. And because they're repelling each other, they settle into an equilibrium state, which is lowest when they're spread out like this. So once again, we have charges on the surface. And then in here, inside the conductor, there are no charges inside. So in other words, this thing is neutral inside. Now I have the other situation where a charged dielectric. Again, because this is important, I'm going to color this to remind you that we're really focusing on this thing right now, is uniformly charged throughout its entire volume, not just on the surface, but also throughout the entire volume with a constant charge density. And we're going to spend a lot of time, for quite some time, on these situations. So here I go. I have a sphere. By the way, I could have drawn a cylinder. I could have drawn a cube. But I have this sphere. And when I look at the sphere, it has a charge density. But the way the charge density sets up here is that it's distributed uniformly, as well as surface charges at the surface. So we're seeing here in this situation that there are charges both on the surface and inside of the sphere in this case. So what we're going to look at now is that we want to determine Q enclosed. So the process of determining Q enclosed is identical to calculating the charge element in chapter 2 when we were integrating electric fields or charge distributions to get the electric field. The process is identical. In each case, or in each of these cases, and we're really going to only pick two here, we are looking to calculate a partial charge within a volume. Now, there is a rare situation where you calculate a surface charge, but that doesn't happen very often. Okay, so if I go back to chapter 2, what did we do in chapter 2? In chapter 2 here is that we calculated a charge element, dq, and the way we did it is that we looked at the charge density, but we ended up calculating some infinitesimal charge because we were integrating. Now in chapter 3, we're now looking at the enclosed charge. Q enclosed. And so what we mean by that is we're talking about the Gaussian enclosed charge. And it all starts with the charge density. So let's jump right into that. So due to constant charge densities, of spheres, cylinders, thick planes, and we can also have planes and line charges. But those are, like I said, those are more rare. One should picture these images. So I imagine that I have a sphere. So when I'm looking at this sphere, it's going to be uniformly charged. So when I'm looking at these charges, I'm going like, yep, I have a uniform charge distribution. But if we're looking at a Gaussian that encloses charge, what we're going to be doing here is that we're going to be looking at a smaller volume of this charge. So then you're going to see here is that this is really Q enclosed right here. I could do the same thing with the cylinder. If I have a cylinder, what's going to happen here is that I'm also going to have a charge distribution here. So when I pick a Gaussian, what we're going to see here is that we're picking a subcylinder that only includes the partial charge of this guy. And so you could see here is that this is also the enclosed charge. So if we're talking about these volumes, then we're saying that we have charge density, which is a constant, and very similar to chapter 2, we then say, what's the total charge divided by the volume of the object. And then we focus on just a tiny bit of partial charge, and we looked at the enclosed volume and how much charge is in that enclosed volume. Excuse me. Or we can look at a surface. So if I look at a surface, even though I'm going to draw this thing thick, it's not thick. Just to show you that it's a plane. And this plane is going to have a uniform charge. And what we're looking at here is that if we're talking about an enclosed charge, we're only looking at a small section of the plane. So we're not looking at a volume. That enclosed charge is not over a volume, it's over a surface. So then we say that eta is a constant surface charge density. And again, we have the total charge over the total area. And then this will be the enclosed charge over the enclosed area. So now let's focus. Now again, I could do this for lines, but I don't think we even see it in this course. I could be wrong. So with dielectrics, there is a dramatic difference since they contain charge inside while conductors do not. Our discussion here is to really focus on dielectrics only. Because as soon as we do a dielectric, we immediately know what the conductor is. So why are we doing this? Gauss's law has our flux, which is E dot dA, and this piece right here is, of course, step one. And we've already done that. So now if I look at the right side of Gauss's law, we have Q enclosed. And so our goal here is to now do this, step two. To calculate Q enclosed, we will pick two Gaussians. The first one is then going to be outside the charge distribution. And in other words, this picks R greater than bigger than big R, and that applies for insulators and conductors. It's the second one that's the most important one. We want to look at inside the charge distribution. So in this case, by the way, I should have said this is to calculate fields outside the charge. In this case, we have the opposite situation. We're going to calculate fields inside the charge distribution. So those are the two cases that we really want to pay attention to. So here we go. So the first one we'll start with is we'll start with the sphere. So if I have a uniformly charged sphere, what do I have? I have two things that I want to look at. I want to look at outside the sphere and inside the sphere. So we have to assume a couple of things. So we assume Q total, radius R, big R, and uniform charge density. Which means rho is equal to a constant. Okay, let's start with outside. So we want to calculate the charge when the Gaussian is outside the sphere. So if I'm looking at this, In this situation, we find here is that the Gaussian encloses all of the charge. Okay, it encloses all of the charge. So now I have, if I draw my charge sphere, and so then I'm looking at my charge distribution. I know it's uniform. And so what I'm doing here is that I'm picking my Gaussian now. So what do I know? Well, if I enclose all of it, there's two things that we should think about. One, this is the radius of the Gaussian, and you could see that it's larger than the radius of the sphere. And then this guy right here is the radius of the sphere. And so we clearly, so if this guy has a total charge of, Q total, then it's obvious that Q enclosed must be Q total. At times, it's useful to rewrite Q enclosed in terms of the charge density. In other words, if I look at rho says that it's the total charge volume over the total volume, which then tells me then I can rewrite the total charge as rho times the volume. But in this case, since we're talking about a sphere, then it's going to be rho times 4/3 pi r cubed. So in other words, I can either write the enclosed charge as just as Q total, but like I said, sometimes it's useful to have it in terms of the charge density. So that's my enclosed charge for outside. So this is true whether I'm a conductor or an insulator. Where it gets interesting is when you go inside. So now we're talking about inside. So we want to calculate the field inside the dielectric. So in this case, the Gaussian only encloses a partial amount. And that partial amount we call Q enclose, a partial amount of the total charge, Q total. So if I draw my Gaussian, I'm inside. So now I'm looking here. Remember, so this is a shell here. And so now I have a charge distribution. So now what I'm seeing here is that I have this. I come in here and I'm going to pick my Gaussian right in here. So what you're seeing here is that that includes not the total charge. It's a smaller amount. So what you're seeing here is that you're looking at this. So this Gaussian encloses Q enclosed. And when you're looking at these distances here, you could see here is that this guy here is little r. That guy right there is big R. And so picture-wise, we're seeing something like this here. What we're seeing here, let me move this over here. So if I look at this thing, the first thing that I see here is that I have an enclosed charge is smaller than Q total, right? Of course, Q enclosed is only part of the charge, not all of the charge. And then if I enclose the enclosed, excuse me, not the enclosed, yes, the enclosed volume is smaller than V total. So yes, V enclosed is smaller than V total of the volume of the sphere because they're smaller. However, the charge densities remain the same. So now, with that in mind, so if I start with the charge density equation, we can solve for Q enclosed. So here we go. So I keep looking at this picture, so that's what I'm going to be looking at. So if I look at this thing, we see here is that I have rho, which tells me I have a constant charge density. And so what I'm seeing here is that I get Q total over the volume total, and that has to equal Q enclosed over V enclosed. But let's color code these, right? Because when I look at this guy, that is associated with the full volume, which doing that. And then the purple ones, these guys are associated with the Gaussian, right? So in this case, this is the total, and this here is the partial. So of course it's smaller, but the charge density is the same. So now what I'm going to do is I'm going to solve for Q enclosed. So as I solve for Q enclosed, I'm then going to have Q enclosed is going to be the total charge. It's going to be V enclosed over V total. So right there, you could see that this is a fractional percentage telling you that it's going to be less than 1. So then if I start putting in my values, I know that the volume of the Gaussian depends on little r cubed. The volume of the full, sphere is big R cubed, which is bigger. So again, I start looking this and it says, what are these guys connected to each other? So the violet tells me that I am doing that. That's with the Gaussian. Now, if I look at the total, it's associated with these guys here. So if I write this out, you're seeing here that now I have a relationship that the enclosed partial charge of a sphere is R dependent. And we'll get more into the physics of why that is, but here's what we're seeing. We're seeing that the enclosed charge is going to be R cubed over big R cubed, which is less than 1, times the total charge here. So that's my charge, my enclosed charge for my sphere. Now let's repeat the process for a uniformly charged cylinder. So this is almost the identical situation as before. So we'll move a little bit faster here. Okay, so what are we going to assume? We're going to assume the same type of things. We assume that we have total charge. It has radius, big R. It has length, L, and uniform charge density, which is rho equal to the total charge divided into the total volume. So let's go here. So 1 here, we're going to go outside the cylinder where I picked my Gaussian bigger than that encloses all of the line. Now, we got to be careful with this. This is a tricky one. So what we're saying here is that the Gaussian encloses all of the charge. So it immediately tells us then that Q enclosed has to be Q total. Now, this is tricky here. So let's see if we could draw the picture here to try to clean this up a little bit. So I have a line. I have an infinite cylinder. So it goes on forever here. And what you're going to see here is that, again, we're looking at this guy. Now, we've talked about this a little bit in step 1, but I'm going to say that I have, again, a uniform charge distribution here. So I have a uniform charge distribution. Now, what I'm going to do here is that I can't see the ends, right? Can't see the ends. But one of the things that we do know is that the flux through the ends of the Gaussian, even though it's shorter, will amount to 0. So now, if I have my Gaussian coming around like this, it doesn't cover the whole line. It doesn't enclose the whole line, but it encloses the charge right here. So you're seeing a partial charge here. So when I say it encloses all of the charge, it's a little bit slippery because it turns out that if I look at this guy, this has a length of L. This guy right here has a radius of big R, and then this one right here has a radius of little r. So what we said in the previous section here is that we don't care about the end pieces because the electric field and the surface area are zero. The only thing we care about is the curved walls. And we'll see here that that leads to a total charge. So I will come back when we do an example and look at that in great detail. 2. So now we're inside the cylinder here. So that means that R is smaller than big R. So in this case here, the Gaussian encloses only a partial amount and this is what we call Q enclosed of the total charge Q total. So let's draw a good picture here. So now here I'm outside, so I'm enclosing all of the charge within the Gaussian right here. But that's different in this situation because now if I look at this scenario here, here's my Gaussian. Now I got to do a uniform charge distribution. So here I go. I'm going to go. So I have a uniform charge distribution. So now my Gaussian is now inside. And what you're seeing here is that I am enclosing some of the charge, a partial charge, not the full charge. So in this situation, that has Q total. This guy has partial Q enclosed. Where, in this situation, we're talking about that this is the length L, the radius is a little bit harder to see here, but if I then come over here and say, here's the edge right here, so I'm looking straight at this thing, and if I look at my Gaussian, which is right here, then what you're seeing here is that I have 2 points that I can think about. One, I have this guy right here. That's going to be my radius R. And then I look at this guy, and that's going to be little r. So those are my radii. So now if I start to put this together here, we said this thing, the same thing with the sphere. The enclosed charge and volume of the Gaussian has Q enclosed less than the total charge, and the volume of the enclosed cylinder here is definitely smaller than the total volume. Starting with the charge density equation, we then have this. We start with rho equal to a constant. That tells me that I have a total volume over the the total charge over the total volume, and that has to equal the same ratio of the enclosed over the enclosed volume. So once again, this represents the total. This represents the partial. So again, if I color code these guys, this has to do with the full cylinder, and these have to do with the enclosed cylinder, which is of course smaller. So now, as we did before, we then solve for Q enclosed. And as I solve for them, I then get Q enclosed, and then I'm going to get the total charge of V enclosed over V total. And this guy should then be Q total. And the area of the volume of a cylinder is pi r squared times its length. And this will be pi r big R squared times the length. So again, color coding this, everything that's violet has to do with the Gaussian that encloses this amount of charge. Everything else has to do with the actual cylinder. So then if I do some cancellations, then we see here is that the enclosed partial charge of the cylinder is then going to be Q enclosed is then going to be R squared, big R squared times the total charge. So now we're done with Gauss's law. Let's go to step 3 right here. It's just everything is now just being put together. So now we're at the final step here. And what we want to do here is apply Gauss's law to determine the electric field function. So now what we do here is that we combine steps 1 and 2, and it looks like this. We see that we have the flux through the Gaussian. And when we did that, we either get we end up doing this guy here, which then tells us that we could then pull out this function where the electric field depends on the area of the Gaussian right there. But on this side here, on the right side, we now have Q enclosed divided by epsilon naught. You could see here is that this right here, this comes from step 1. By the way, let me be careful here. This here is step 1. This guy right here is step 2. So we're just putting these guys together. So then Gauss's law says that 1 can solve for E of R, which is then going to be plus or minus Q enclosed epsilon naught divided by the area of the Gaussian. And then this is our result of Gauss's law. So if I have a sphere, I know how to do this. If I have a cylinder, I know how to do this. And if I have a cube, I know how to do this.